What's up YouTube, my name is Nick, and in this video I'll be trying to recreate Mark Setrakian's incredible Axis robot on a hobbyist budget. Seriously, look how cool this is, it's like the globe is floating. Everyone in Tested's comments seems to want their own. If I manage to recreate this, I'll be open sourcing the design so that anybody can 3D print it. To start this project I first need to study the original robot in detail. The first thing I notice is the servos. Looks like Mark went with the Dynamixel MX64AR. At $350 a piece, I will absolutely not be able to afford 15 of these. So I found some cheaper ones. These are the LX16As, and they're only 20 bucks a piece. Thank you, China. After looking over the specs, I figured these will probably work, so I bought 15 of them. Next up are the 3D printed parts that make the fingers look like fingers. I spent a long time trying to make these look as sexy and curvy as Mark's, but it turns out I can only model things with straight lines. Here's what I came up with. They're not perfect, but I'll call it good for now. Time to dust off my trusty ANET A8 and print my first low poly finger. After a few revisions, it looks like it's all fitting together well. So I made 4 more and a palm to hold them together. Now it's time for the hard part, the math and programming. I'll be using the incredible ESP32 along with MicroPython to control this thing. Thanks to this library made by Cecilva 1998, I was able to get my first servo moving. His library allows me to command each joint to spin to any angle I want. Now how on earth do I make all 15 work together to do this? Let's start by defining a coordinate system. The origin will be the center of the palm, X is left to right, Y is forward and backward, and Z is up and down. Now what I need is a way of commanding each fingertip to go exactly to the coordinates I want. And to do this, I'll be using a trick called inverse kinematics. I need to come up with a function where the input is XYZ coordinates, and the output is the angle each servo needs to go to get the fingertip to those coordinates. Let's start with considering just one finger and only these 2 motors, so it's a 2D problem for now. If I want the fingertip to go here, -80, 100 in our 2D coordinate system, since I know the lengths of these lines, I can do a bit of sine and cosine shenanigans, and I find that the angles need to be 18 degrees and 123 degrees. Now I can send the real motors to those angles, take some measurements, and looks like the tip went where I wanted it. After drinking many liters of coffee and doing a similar problem in all 3 dimensions, I now have the Python function I was looking for. This function lets me send the fingertip to any XYZ coordinates I want. So now I can do things like make it draw a circle on a horizontal plane, and make it draw a circle on a vertical plane. The trigonometry gods have had mercy on us, and the inverse kinematics is complete. But our robot can't quite do what Mark's does yet, so it's time to study the motion of his robot a bit more. There are a few very important things I notice. 1, only 3 fingers touch the globe at a time while the other 2 are retracting. The only time 4 fingers are touching is very briefly when 2 are passing off to each other. 2, the motions are all looping through the same motion shown in this graph. 3, the phase angle between motion of adjacent fingers is 144 degrees. And 4, Antarctica must be really heavy. Otherwise, how would the globe be staying upright? From a top-down view, this is the motion the fingers need to make. At any given time, 3 fingers must be moving along these paths at the same speed, while the other 2 are retracting and returning back to the start of their path. Since 3 fingers must always be touching the globe at a time, each finger must spend exactly 60% of its time pushing the globe around, and the other 40% of the time returning back to its start. These fingers can't all be doing the motion exactly in sync. The motion needs to be offset from one finger to the next, and the magic number is 144 degrees, or 2/5 of the period. This seems like a pretty solid motion plan, so let's code it. It's a little choppy, but after investing tons of time into this, it's incredible to see it finally working. After some metaphorical polish and a nice stand, it'll be the perfect supervillain side table decoration. Up to this point, I've been using this human-shaped palm to hold the fingers together. But as my roommate Josh said, there's really nothing human about this. So I designed a more symmetrical version of this palm, which is more similar to Mark's Axis 2. I like this one a lot better. I wrangled with the code a little bit and managed to smooth out some of the bumpiness. Then I poured some plaster of Paris into the globe to keep Antarctica at the bottom. The result is a new buttery smooth motion. Mark's robot is really epic, but the cherry on top is the way he can use this joystick to move the globe around while it's spinning. I definitely had to add this, so I found a similar joystick on Amazon and got to work. The joystick is basically just 3 potentiometers, so all I had to do was map the potentiometer positions to the XYZ positions of the center of the circle in code, and voila, it works. Well, at least most of the time it does. With the coding complete, what I need now is a stand to house all the electronics. I designed this stand to be printed in just 2 pieces and locked together. Since I have some plaster left over, I'm pouring some in the bottom of the stand to keep the thing from tipping over and walking away on me. I also need to ditch this ugly breadboard and move the parts to a proper PCB. I designed this one in KiCad and sent it to JLC PCB to get printed. A couple weeks later, I got 5 beautiful circuit boards in the mail. JLC soldered some of the small parts on for me, but I'll need to do the rest by hand. I'll go over what these parts are while soldering them on. This IC that came on the board is a logic level shifter. My microcontroller uses 3.3 volt logic and the motors use 5 volt logic, so this allows them to talk to each other. First to attach is the ESP32. This of course is the brain of the project. Next are some Mongo capacitors for one of the buck converters. This is the 8 volt buck converter. It converts 12 volts from the power supply into the 8 volts the motors need. Here are some connectors for the 12 volts in and for the joystick. Motor connectors for each finger, a 5 volt buck converter for the ESP32, a capacitor for that buck converter for good measure, and finally a tri-state buffer. It allows the dual wire UART from the microcontroller to communicate with the single wire UART that the motors use. And this custom board fits perfectly in the top of the stand. Now this sure as hell beats the breadboard I was using before. After a bit more assembly, I think it might just be finished. I'm super stoked with how this turned out, and if you like it too, go to my GitHub linked below and print your own. Every file you need should be on there. This includes a bill of materials, the MicroPython code, the STL files for 3D printing, and the circuit board designs. If you liked this video, please smash the like button an odd number of times and leave a comment below about what you think I could add to it. I think it could use some RGB. See you in the next video.